To start designing algorithms for a cluster or a supercomputer, you're going to need a machine model. How about this one? In this model, a machine is a collection of nodes connected by some kind of network. Each node consists of a processor connected to a private memory. By private, I mean that the node can only directly read or write its own memory. It can't directly access the memory of other nodes. I'll refer to this type of machine as a distributed memory machine. Now, this abstraction of private memories is critical. It implies that to share data, nodes will have to send messages to one another. So for example, suppose this node wants to send data to this node. The only way to do that is the sender, or source, has to package up a message and then put it on the network. So this message will have to find some path through the network to get from the source node to the destination node. In contrast to shared memory, where we read and write shared variables, this style of parallel communication is called message passing. Now, this machine model has a few simple rules. The 0th rule of the model is you never talk about the model. By that, I mean you need to master and internalize these rules. Okay, so what are the real rules? The first rule is that you should assume the network is fully connected. That means there's always a path from any node to any other node in the network. The second rule is that the network links are bidirectional. What does that mean? Well, suppose I have two nodes in the machine and they're connected by a link. Bidirectional means that the link can carry a message in both directions at the same time. So while one message is going this way, another message can be going this way. The third rule is that you will allow a node to concurrently perform at most one send and one receive at a time. This rule is important because it affects the cost of communication. So for example, suppose this node wants to send a message on each of its outgoing links. In order for this node to send 4 messages, it's going to have to send them one at a time. By contrast, it could do one send and one receive simultaneously. The fourth rule is about the cost of a simultaneous send and receive of n words. So suppose this is our computer. And let's further suppose that this node wants to send a message to this node. There are several different paths. Here's one path, and here's another. Regardless of which path the message takes, rule number 4 says the following. The time to send this message, if it contains n words, is a constant alpha plus another constant beta times the size of the message. In other words, the cost of sending the message is linear in the message size. Now, it may seem strange that this cost somehow is independent of the path that's taken. Now, that's not entirely true, and I'll clarify a little bit later in the lesson. For the time being, let's accept the formula as stated. Now, the formula has two terms. The first term is called the latency, and it has units of time. It's a fixed cost that you pay no matter how large the message is. The second term has a parameter beta. Beta has a name. We'll call it the inverse bandwidth. It has units of time per word. You'll think a little bit more about where this cost model really comes from momentarily, so just sit tight. One subtlety is that this fourth rule really only applies when there are no messages competing for links. So we have a fifth rule which tells us what to do when messages are trying to go over the same link at the same time. This situation is called congestion. This rule says if there are k messages simultaneously competing for a link, then in terms of the cost of the message, we'll change only the beta term. And in particular, we'll multiply it by k. For instance, let's consider this link that connects these two nodes. The last rule governs what happens if two messages try to go over the same link simultaneously. So suppose there's a red message going this way and a blue message going this way. The last rule says that the effective cost of this operation is the same as if the data transmission part, which is the beta term, was serialized over the link. So if these two messages are being transmitted in parallel, instead of observing a parallel execution time of alpha plus beta n, supposing that the messages are the same size n, what you'll see instead is a cost of alpha plus beta times n times 2. Okay, so take a second to look at these rules and commit them to memory.